My name is Danielle Alverson, and I am from Kansas City, Missouri. I will be a senior mechanical engineering major at the University of Arkansas. For the 2019 SURF program, I worked in the Materials Science and Engineering department in the Professor Hennick's research group. For the past 9 weeks, I've been using computational material science to help discover new battery materials.
I have learned to code with Python and maneuver my way in bash commands to work with the University of Florida supercomputer called HyperGator. We use HyperGator to run DFT, density functional theory, calculations. The Hennick group uses VASP that uses quantum mechanical calculations to find, in my case, ground state energies. What I have been doing is using programs to locate interstitial sites within layered materials to insert lithium ions systematically so that 1, they are not touching each other, and 2, are occupying the furthest distance apart. At first, the software Pilota Defects was used to find interstitial locations to insert lithium ions into layered materials. However, the program used unique Wyckoff positions to create Voronoi volumes. Then takes symmetrically inequivalent regions to choose for the interstitial sites. Unfortunately, for our application, the program cannot systematically sort the volumes from greatest to least, nor the furthest distance apart, and that became a problem because some of the sites were either too small or too close to one another. Now we use MP interfaces, and a code created by a former researcher in the Hennick Research Group, Michael Ashton, who created a fine interstitials program which uses Delaunay triangulation that sorts by volume. With a little manipulation of the code, it can systematically insert lithium ions sorted by the largest volume and then by the furthest distance apart. Once lithium ions are inserted based off different percentages of lithium insertion, the structure can then be relaxed using DFT to find the ground state energy. This ground state energy can be compared to the base layer material energy and the lithium ion energy. This comparison can then create a convex hole, which is used to find the thermodynamically ground state phases of the lithium ion compound at any of its compositions. We were able to create a software that can systematically sort ions into layered solids. The graphite anode held comparable results to those of experimental data in a paper concerning lithium insertion in graphite, where the top voltage that can be reached is 0.25 volts at 15% lithium composition. Computationally, 0.18 volts was attained at 14.3% lithium composition. 3 other layered solids were investigated based off their low densities. From the comparable computational results of the graphite anode, it can be assumed that the convex holes of these materials are trustworthy. Out of the 4 materials that were tested with this method, magnesium hydroxide had some difficulty having the lithium ions inserted into its structure, and the convex hole diagram was not a success. However, graphite, carbon nitrate, and Mg2H2O3 yielded good and promising results.
This summer has definitely been one to remember.
From the beautiful campus to all the great outdoor activities to do here, I have met great people not only with the SURF program, but also in my research group. I've experienced paddleboarding, many board games, and even had a spontaneous trip to Jacksonville. There has been so much fun learning about new things in terms of research, the GRE, and just getting more educated about the responsibilities of a PhD student here at the University of Florida.
I have loved my summer here, and I look forward to continuing my education here at the University of Florida.